the binomial expansion, the binomial coefficients, and Pascal's triangle. So in this video I'm going to review some basic theorems about binomial coefficients which are already studied by us in the module called Counting and Probability. So let me start with the first theorem, binomial coefficient with 0. So what it says is that for all n in the set of all natural numbers, n choose 0 is always 1. Okay, so for example, to give you an example, it says that 0 choose 0 is 1. It also says that for example 3 choose 0 is 1. Okay, so how to prove it? Imagine you use the definition. So n choose 0 is nothing else than n factorial over 0 factorial times n minus 0 factorial, according to the definition. So n minus 0 is n factorial. And you see that these two cancel out. This leaves 1 here in the numerator, and 0 factorial is 1 by definition. So it's 1 over 1, which is 1. So all such coefficients which have 0 in the bottom of it, in the bottom row, are always equal to 1. So this is the first theorem, binomial coefficient with 0. The second theorem has to do with binomial coefficient with self. So for all n in the set of all natural numbers, we have n choose n equals 1 always. So for example, 5 choose 5 should be 1. Also, 7 choose 7 is 1. Okay, so how to prove it? Again, start with the definition. N choose n is, according to the definition, it's the n factorial from the top over the factorial of the number in the bottom, so it's just n factorial, times this minus this factorial, which is 0 factorial. And you see again, this cancels with this, there is 1 in the numerator, and this 0 factorial is 1, so we have 1 over 1, which is 1. So these coefficients have to be 1. Now we have the binomial coefficient with 1. So for all natural numbers, for all n in natural numbers which are greater than or equal than 1, n choose 1 is always n. For example, 1 choose 1 is 1, or 3 choose 1 is 3, and so on. Okay, we can't have 0 choose 1, this would be nonsense. So there is this condition, hence, okay, n has to be greater than or equal to 1. Now, to prove it, let us use the definition of the binomial coefficient again. According to the definition, it's n factorial over 1 factorial times n minus 1 factorial. But now you can capitalize on the definition on the recursive definition of the factorial. N factorial is nothing else than n times n minus 1 factorial divided by 1 factorial, which is just 1, times n minus 1 factorial. And you see these two cancel out. So we have n over 1, which is just n. And this is the proof. This is the proof of the fact that n choose 1 is always n. The fourth theorem, binomial coefficient with self minus 1. Okay, so what it says, for all natural numbers n which are greater than or equal to 1, we have n choose n minus 1 is always n. So what, for example, says that 5 choose 4 is 5, or 7 choose 6 is always 7. Okay, so let me prove it. In general, n choose n minus 1 combinational number equals, according to the definition, to n factorial over n minus 1 factorial, so it's the factorial of this number here, which is usually called r, times the factorial of this minus this, so times n minus 1 factorial. So you see, again, I can use the recursive definition of n factorial, so this is n times n minus 1 factorial divided by n minus 1 factorial, And here in the square brackets, n minus n is 0 and minus minus 1 is 1, so we have just 1 factorial there. These two cancel out and we have n factorial over 1, which is n over 1, which is n. So this completes the proof of this thing. The fifth theorem, symmetry rule for binomial coefficients. So there is some kind of symmetry there. For all natural numbers n and for all natural numbers r such that n is greater than or equal to r, the following is true. N choose r equals n choose n minus r. To give you an example, it says, for example, that 7 choose 5 is always the same as 7 choose 7 minus 5, which is 2. Sorry. So these two are the same. Or we can say that 10 choose 2 is the same as 10 choose 10 minus 2 is 8. So these two are the same. So to prove this, let me start with the definition. N choose r, according to the definition, is n factorial over r factorial times n minus r factorial. According to the definition, the number on the right-hand side is n choose n minus r, and according to the definition, it's n factorial over n minus r factorial times, and then I should have n minus r factorial, n minus r factorial. So I have used square brackets to simplify. So you see that what you get here is it equals n factorial over n minus r factorial times, and here n minus n is 0 and minus minus r is r, so we have r factorial. Now if you compare this and this, you see that the fraction here and this one are the same. So it completes the proof. This number is equal to this number. So this is the symmetry rule for binomial coefficients. Finally, the last theorem, sixth theorem, Pascal's rule for all natural numbers n and for all natural numbers r such that n is greater than or equal to r plus 1. It implies that this should be true. So to give you an example of such situation, let us use n equal, say, n equals 7 and r equal to 3. Okay, so it says that n plus 1, which is 8, choose r plus 1, which is 4. So 8 choose 4 should be equal to n choose r, which is 7 choose 3, plus n choose r plus 1, 7 choose 4. So it says that the binomial coefficient 8 choose 4 is the sum of two binomial coefficients which have 7 on the top, and one has 3 and one has 4. Okay, so to prove it, what we need to do is to show that the left-hand side is equal to the right-hand side. And this can be achieved in numerous ways, but I'm going to use this time the definition again. So let me try to evaluate n plus 1 choose r plus 1. If I want to evaluate this, I will use the definition. According to it, it's n plus 1 factorial over r plus 1 factorial times, and now I need to have n plus 1 minus r plus 1. n plus 1 minus r plus 1. This should be in brackets, however. Okay, like this. So, according to the definition, this is n plus 1 factorial over r plus 1 factorial. And here I have 1 minus 1, which cancels out, so the only thing that remains is n minus r factorial. Like this. I will leave it as it is at the moment, and I will try to evaluate the sum of these two factorials on the right hand side. So not factorials, by combinational numbers. So n choose r plus n choose r plus 1. This should be equal to, so the first one is n factorial over r factorial times n minus r factorial, plus the second one is n factorial over r plus 1 factorial times, and I need to have n minus r plus 1 factorial, which is just n minus r minus 1 factorial. So this is the sum, and I have, if I want to calculate it, of course, what I need to do, I need to have the same denominator. I have to find a common denominator here. Now, you see there is r factorial, so here is r plus 1 factorial. So it might help if I multiplied this by r plus 1 and here also by r plus 1 to create r plus 1 factorial here. Then you see that this is n minus r factorial and this is n minus r minus 1. So it might be helpful if I multiplied this by n minus r and this also by n minus r. Hence, these two would form n minus r factorial. Now, having the same denominator, I can rewrite as follows. So the same denominator is r plus 1 factorial, this already here, times n minus r factorial. This is the same here because this is this term here, and this times this is n minus r factorial. Okay, and on the top we are going to have n factorial times r plus 1 plus n factorial times n minus r. Now on the top I can take n factorial out, and here in the bracket I will have r plus 1 plus n minus r divided by r plus 1 factorial times n minus r factorial. So you see we have the bottom the same as this one, and on the top r plus 1 minus plus n minus r. These r's, they just cancel out, and I have then n plus 1 here. And this factor, n plus 1, multiplied by n factorial, gives me n plus 1 factorial, according to the definition of factorials, divided by, and what I have here is r plus 1 factorial times n minus r factorial. And when you compare those two, you see that they are the same. So it means that the left-hand side and the right-hand side of this equation are the same, and this completes the proof of this Pascal's rule. Okay, so simple it is. Now, the second part of this video will be devoted to the understanding of the connection between these numbers, these binomial coefficients, which have the properties proved in these 6 theorems, and between the Pascal's triangle. So we already know what the Pascal's triangle is. It's a triangle which is generated using this simple rule that always you start with 1 and like this, and then when there are two numbers, the number below them in the middle is their sum. So you have 2 and 1 on the sides. Again, we have two numbers here, their sum is 3, I write it in between, 2 and 1 is 3, and complete with 1s. 1 and 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and finish with 1s. And I can do also the fifth line, so it's 5, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and again 1 on the side. So these numbers are the binomial coefficients, the coefficients in the binomial expansion. You already know that these are there, but at the same time binomial coefficients are these numbers defined by the definition of n choose r, and they have these properties. So what I want you to see is the connection between these numbers here in this triangle and binomial coefficients. So this number 1 on the top is nothing else than 0 choose 0. 0 choose 0 should be 1 according to this theorem that n choose 0 is always 1. So also 0 choose 0 is 1. Then the number below here, this 1, is 1 choose 0, and this one is 1 choose 1. According to theorem 1, 1 choose 0 must be 1. According to the theorem 2, n choose n, 1 choose 1 should be 1 also. So this is also 1. Now let me go for the third, actually zeros first, second row. In the second row we have 2 choose 0, which is this one. We have 2 choose 1, and we have 2 choose 2. According to the first theorem, this is 1, and this is 1 according to the second theorem. How about this number? This number, 2 choose 1, should be the sum of this and this. And this is actually the thing which is claimed by this last Pascal's rule, which says that n plus 1 choose r plus 1 is always n choose r plus n choose r plus 1. So 2 choose 1 is 1 choose 0 plus 1 choose 1. Okay, so we can replace 2 choose 1 by 1 plus 1 choose 0 plus 1. And according to the theorem, to the Pascal's theorem, this is 1 choose 0 plus 1 choose 1. Okay, like this. So this number is the sum of these numbers above it, and it's the claim of the sixth theorem, the Pascal's theorem. Now so this was the 0th first line. Now that this is the second, let's go for the third line. Third line starts with 3 choose 0, then we have 3 choose 1, then we have 3 choose 2, and we have 3 choose 3. So the first theorem tells us that 3 choose 0 must be 1. 3 choose 3 is 1 according to the second theorem, okay, because n choose n is always 1. How about these two numbers? 3 choose 1 should be this plus this, and it really is. 3 choose 1 can be understood as 2 plus 1 choose 0 plus 1, and it is, according to the Pascal's theorem, it is 2 choose 0 plus 2 choose 1. Okay, so this is true. This plus this is 3 choose 1. Also, it works for this number. 3 choose 2 is this plus this. You can check it yourself. Okay, fourth line will have 4 choose 0 at the start. Then we have 4 choose 1. We have 4 choose 2. We have 4 choose 3. And we have 4 choose 4. The numbers on the sides are 1, and this number is the sum of these two. This plus this is 4 choose 1. This plus this is 4 choose 2. This plus this is 4 choose 3. Check it yourself. This is really what the Pascal's theorem says. Now the fifth line starts with 5 choose 0. Then there is, in between those is 5 choose 1. 5 choose 1. Then we have 5 choose 2. We have 5 choose 3. We have 5 choose 4. And 5 choose 5. Okay, so this is the connection. This is the connection between the combinational numbers defined by the definition n choose r equals n factorial over r factorial times n minus r factorial, and the combinational coefficients or binomial coefficients in the binomial expansion defined by the Pascal's triangle. This is the connection, and I have already shown you what is the consequence of the first theorem. The first theorem says that these numbers here, all these numbers here on this side, have to be ones, which really they are. These are ones. The second theorem tells you that these numbers on the right hand side, 1 choose 1, 2 choose 2, etc., have to be 1, so these are only ones. Moreover, the third theorem tells you that the numbers which have 1 in the bottom row are always the same as the number on the top. So it tells you that these numbers, let me use the color, it tells you that these numbers here are always the same as the number on the top, so 2, 3, 4, 5, etc. You see, okay, so this is what the theorem 3 tells us. 2 choose 1 is 2, 3 choose 1 is 3, 4 choose 1 is 4, 5 choose 1 is 5. Then it was the third theorem. Now there was the fourth theorem telling you that the binomial coefficient of self and self minus 1 is always n. It tells you that these numbers here should be always the same as the numbers on the top. 2, 3, 4, 5, you see here. Okay, so this is what the theorem number 4 tells us. And then there is the theorem 5 about the symmetry rule for binomial coefficients. So what is the consequence of this symmetry rule on these numbers in the Pascal's triangle? Well, if you look at this triangle, you see that it's symmetrical in the sense that when there is 5 here, it's also here. 4, 4. 6 is in the middle, so it's just ones there. But if there is no number in the middle, then these numbers here must be the same. Okay, so the left side and the right hand side of the Pascal triangle are always the same numbers. So for example, 4 choose 1 must be the same as 4 choose 3, or 3 choose 2 is the same as 3 choose 1. So there is this symmetry, axial symmetry with respect to the vertical axis. And finally, the last Pascal's rule is the rule that generates the Pascal's triangle, and it's the rule that tells you that the number, any binomial coefficient in the Pascal's triangle, which is not on the sides, is the sum of the two coefficients which are above it. Okay, so when they are above it, they have the number on the top which is 1 less than the number on the top of this coefficient, and this one number is 1 less than this one, and this is the same. So for example, 4 choose 3 is equal to 3 choose 2, so this number 3 is 1 less than 4, 2 is 1 less than 3, plus 3 choose 3. This 3 is 1 less than 4, and this 3 is identical with this. So this is the statement of the Pascal's theorem. Okay, so this, what we did in this video, will now enable us to do the following. We will state the binomial expansion using binomial coefficients as combinatorial numbers, and we will then be able to easily solve problems which involve expansions of the expressions with higher powers than 3, 4, or 5. We can take power 12 or 15 or 70 and so on. And that's it for the video.